report over circuits. So a table of contents, we have our introduction, and then some lab results. Then we'll go on to questions and a conclusion. So the introduction of this lab was we wanted to predict and measure behavior of conventional currents and DC series circuits and RC circuits. And we use this using a program that will let us model these. So important concepts and formulas. The first is Ohm's law. We use to relate the resistance and potential drops in current. We use Kirchhoff's loop rule. And then we also used RC decay formula, which describes how a capacitor loses voltage over time. So what is this lab? Using the principles of energy conservation, loop rule, and current conservation, charge conservation, plus defined of steady state, you will predict the behavior of circuits containing resistors in series and parallel. Use multimeters to measure the actual values in conventional current and potential differences in the circuits. And examine the behavior of ohmic resistors and capacitors. So into our results. Here you can see some of the circuits that they asked us to design. Since this is a single steady state loop, the circuit charge is conserved, meaning our ammeter reads a uniform 2.02. Using Ohm's law, I measured the voltage drops and it yielded exactly 100 ohms resistance for the resistor and then 47 ohms for the other. Our next slide shows the path that the lab wants us to measure our voltage using a voltmeter, and these are the results from it. You can see how it all adds up to 3, which is the charge of the battery. And then here is some time constant verification. Using slope from the graph and some experimental data. My experiment time came out to about 6 seconds, which is really close to our theoretical value. You can see some of the more time in this one. This was the discharge of the capacitor over time. And you can see how the line of best fit is very close to the experimental value, which goes back to this one. You can see based on these different time measurements, this is the results I've got. Next, some questions. So, what if you were doing this experiment in real life and used an actual ammeter instead of an ideal simulated ammeter? What's the difference about a real ammeter? How would you know it would affect the circuits you hooked it up to? So to answer this question, in an ideal simulation, an ammeter is modeled to have exactly 0 internal resistance so that it doesn't interrupt the circuit flow. However, a real-life ammeter must possess a small non-zero internal resistance in order to function and sample the current. So if you hooked it up to a real ammeter in circuits in series for a circuit, it would add some resistance, and by Ohm's law, the total increased resistance would cause actual current flowing through it to be slightly lower than what our ideal predicted model would have had. We also would have had tiny voltage drops across the meter itself rather than the absolute 0 volts we saw. And then our second question, what if you were doing this experiment in real life and used a real battery to charge a real capacitor with no resistance in the current? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life and explain? So our second question, if we were to plug in a resistance of 0 into our equation, the time constant would be like 0 seconds. So our ideal model predicts that the capacitor would charge 100% instantaneously. But in real life, we can't have 0 resistance, so without a resistor component, real copper wires would have negative resistance, and the real battery cell has an inherent internal resistance, which means actual time constant would be slightly above 0. Capacitor would charge fast, but not instantly, like theoretically. And then in real life settings, this will create a temporary short circuit. The massive immediate spike in current could blow a fuse or something. It can just cause battery overheat and wires to melt. And to conclude, things that could have gone wrong in my data was human error, like timing correctly. Since this is all simulated, it's very unlikely that the actual hardware would be wrong, but clicking and timing the voltage is what could be an issue. Thank you.